Welcome everyone at the last tutorial. A few things about the tutorial itself. So first of all, entropies is an extremely broad topic. Basically, the whole quantum Shannon theory could be presented under this title. Obviously, we won't do that. If you want to know more in this direction, then you can see, for instance, previous QIP tutorials by R.M. Harrow and Patrick Hayden. And I will also give some textbooks on the next slide that are worth checking out. So I think there are people in the audience who are actually working with entropies and probably know more about entropies than myself. But this tutorial is aimed at students who have been less exposed to entropies so far, right? So this is really a basic introduction into entropies. And I prepared quite a big amount of material. I will see how much I will be able to tell. But I also prepared a lot of exercises. So if you are really interested in the topic, you can just work yourself through the exercises. And I think it's really instructive to do so. In the first half, they should be possible to do with basic knowledge in quantum information theory. Okay. And the references are very, very far from being complete. I will give some more references but basically, I would like to refer to the textbooks on the next slide for references. Okay. So this is the user's guide for this tutorial. And here are a few textbooks which I can recommend very much if you are interested in this topic. As you can see, they are fairly recent. And they are, in some sense, complementary. So they are covering different aspects of the same topic. OK, let's start. So to warm up, I will talk about something that probably most of you have seen at some point, which is Shannon entropy. So the question which started information theory, basically, and what Shannon asked in 1948, is how to quantify the information gained by learning the outcome of a random event. Right? So the possible outcomes are in a set X. They happen with some probability Px. Maybe I should start. I should wait a little bit until everyone is settled, because it's a little bit chaotic in the background. Well, anyway. And to quantify the information, we can introduce the concept of surprisal. So basically, we think that an event is more informative if it is less likely to happen. Okay. And we quantify this with a function that is monotone decreasing function of the probability. And if the event happens with probability 1, then we are not at all surprised, so it should take the value 0. Okay? And for any such function, we can define the average surprisal with this formula, which we can also interpret in a dual way as the uncertainty about the outcome before it happens. Okay? And Shannon's proposal was to take f to be minus logarithm, which gives us this formula, which is the very well-known Shannon entropy formula. And the question is, why is it so well known? So why do we know it very well and not other choices of f? And the reason lies in its operational interpretation that it obtains from source coding, which I will briefly describe. So assume that we repeat this random event many times, and we want to encode the outcomes in bit sequences. Okay. So we take a sequence of n outcomes, and we want to encode it into a sequence of bits of length kn. There are two basic ideas that Shannon introduced, is that we can use block coding, so we are coding long sequences, and we allow a small error probability epsilon in the recovery. And whoops, I'm always going the wrong direction. Under these conditions, what we can say is that if you are looking at the error, so that the decoded sequence is not equal to the original, and we look at this probability, and we want this error probability to be under a threshold epsilon. We want to minimize the length of this bit sequence. This is the most economical coding. And it turns out that if we allow the block length to be arbitrarily large, then the optimal bit length per symbol is going to be arbitrarily close to the entropy, to the Shannon entropy. So this is Shannon's fixed length source coding theorem, and this gives a so-called operational interpretation of the Shannon entropy. Okay. As the minimum number of bits per outcome needed to reliably store the outcomes in the asymptotics. Just to clarify some concepts here, so the operational quantity here is the minimum number of bits needed to achieve epsilon error. So this is what's of practical relevance to us, right? Because storing costs money, we have to write the data somewhere, and we want to minimize this cost. Okay. And the other quantity that appears here is the entropy, which we call an entropy quantity or information measure. And many other problems that we study in the rest of the talk are going to be of this nature. And the general picture is that information theoretic problems have an operational side and an entropic side. Okay. And coding theorems connect the two, just as we have seen in Shannon's source coding theorem. And in this way, they give an operational justification to use these entropy quantities as information measure. Okay. So this is the general picture that we will keep in mind in the rest of the talk. And the question is if there are any other relevant information measures other than the Shannon entropy. And of course, the answer is yes, otherwise I would not be giving this talk. So let's see a few others that you may have seen before. One is the so-called conditional entropy, which is just the difference of the entropy of a joint distribution minus the entropy of one of its marginal. And it gets its operational relevance from source coding with side information. I'm not going to talk more about that. You can look it up if you're really interested in it. The other one is the mutual information, which again can be expressed by the Shannon entropy. It's just again, we have a bipartite distribution. We take the entropies, the sum of the entropies of the two marginals, and we subtract the entropy of the joint distribution. This gets its operational interpretation more or less from channel coding, more or less because we have to take an optimization over input distributions to the channel. And then this is the input distribution, and this joint distribution is what is created by the channel between the input and the output. Okay. So these are some information measures that we can build from the Shannon entropy, and they do have some operational significance. And there are other information measures, so-called rainy entropies. And they emerge when we are looking closer at these coding theorems and look at error exponents. I will explain in more detail what this means. And the aim of this talk will be to give an introduction to the most relevant ones of these information measures. And obviously, we are interested in the quantum case. Okay. So this is the warm-up. This is the philosophy behind, or my philosophy behind studying these entropic quantities, which I think is the main philosophy of Shannon theory also. Okay. And the plan of the talk in the first part, we are going to derive abstract information measures from distance-like quantities on quantum states, right? So we are going to introduce so-called divergences and derive information measures from these. And I will only give a few very simple examples that you can very easily verify the properties of. And in the second part, we will focus on rainy information measures and their applications. Okay. The first part should be quite elementary and hopefully easy to follow. The second part will be more dense in information and probably a little bit more advanced. Okay, so let's start with the first topic, general divergences and simple examples. At the beginning, we define a divergence in the most general possible way. Namely, it's a function that takes two positive semi-definite operators and assigns a number, which might be plus infinity. And it should be defined on every finite dimensional Hilbert space simultaneously. Let me introduce a few notations. So B of H will stand for the linear operators on H. Index SA will denote self-adjoint operators, and the plus will stand for non-zero positive semi-definite operators on this Hilbert space. So these are probably all very familiar. And a few examples that you can keep in mind while we are talking about this abstract theory. One that you have certainly seen is the trace norm distance, which is used everywhere in quantum information theory. The other very popular one is the fidelity, which is defined by this formula. And from the fidelity, we define another kind of divergence, which we will call the sandwich one-half Rényi divergence for reasons that will become clear later. And this is just a simple modification of the fidelity. Okay, and define this way. So these are well, basically two examples, 2.5. Another one which is going to be important for us is the so-called max relative entropy, or sandwich-Rényi divergence with parameter plus infinity. I use this notation. Again, it will be clear later why this is the notation. And this is defined by taking two positive semi-definite operators and looking at the smallest positive constant such that we have this domination. This means that the difference is positive semi-definite. And actually, there is an explicit formula for this. So it is quite easy to compute. And let me introduce a few conventions that we will use later in the talk. So you see negative powers here and zero power. What do they mean? If you have a positive semi-definite operator, then we can take a spectral decomposition. So these are the eigenvalues. This is an orthonormal basis of eigenvectors. And we define powers of such an operator by only considering the strictly positive eigenvalues of the operator, right? And we take arbitrary real powers of this. So in this way, we can take arbitrary real power of positive semi-definite operators. And in particular, the power -1 is going to be the generalized inverse. And this power 0 is nothing else but the projection onto the support, which is just the subspace spanned by all the eigenvalues with all the eigenvectors with strictly positive eigenvalue. Okay. So these are just some conventions. And later, when you see negative powers, we always work with this convention. Okay, and the one, last but not least, example is the relative entropy, which is another very, very popular divergence, and which you have probably seen already in various contexts, introduced by Umegaki quite some time ago. It is defined by this formula. Okay, and again, we take the logarithm only on the support of these operators. Okay, so these are 4 examples that we can work with for the rest of the tutorial. And of course, we defined divergences in this very general way, but they will be interesting and useful for us if they satisfy certain properties. So let me go through these properties which we want a divergence to satisfy. So first of all, we want to consider it as some kind of distance or distance-like quantity on quantum states. So we want it to be positive or take non-negative values, and if you put the same state in it, then it should be 0. And it will be strictly positive if this is the only case when it can take 0. Okay, so that's positivity. We like if it's additive. So if you take tensor powers, then it's just n times the divergence of the single copy operators. In the context of thermodynamics, this is extensivity of the quantity. And indeed, we will see it's related to the extensivity of entropy. We want it to be stable. So if you couple an extra system in the same state to both of the states, then this divergence shouldn't change its value. And the most important and the most difficult property to verify is monotonicity, which means that the value should not increase if we act with a completely positive trace-preserving map on both of the operators. Okay. So we want to somehow think of this quantity as the distinguishability of these two states. And we think that if some kind of noisy channel acts on these states, then the distinguishability should not increase. So this is a very, yeah?
Don't have a symmetry requirement?
No. So these are not real distances. They are not metrics, except for the trace norm distance that I showed in the beginning. But actually, we are not going to be so much interested in the trace norm distance. So apart from that, all the others are going to be not symmetric. Okay. So this is more like philosophy or an idea behind, but they are not real metrics. In some contexts, the relative entropy behaves like the square of the Euclidean distance. But that's not going to be important for us now. Okay. And a technical condition is that it should satisfy this logarithmic scaling property. So if we multiply both arguments by different positive numbers, then we should get this relation. There is no intuitive picture behind why this should be satisfied. But we will see that all the divergences that we are interested in satisfy this property. And it will be actually quite useful in certain situations. Okay. And here's your first exercise for the break. Check that all these quantities that we have introduced before as examples, they satisfy all of the above properties. And actually, they satisfy a stronger monotonicity property, namely with positive trace-preserving maps. So you don't have to assume complete positivity. Now this is not, I mean, you should not, or well, if it's very good if you can solve this exercise, but you are not expected to solve all of the exercise, because monotonicity for this quantity and for the relative entropy is very far from being trivial. For this one, it's from the definition. For the monotonicity, you can just look at Niels and Chuang. There's a very nice exposition about the properties of the fidelity there. And for the monotonicity of the relative entropy, it's related to a lot of very important things in quantum information theory, and we will discuss in detail later. Yeah?
So in the definition of D infinity, there was some other norm. Can you just briefly define the norms that you're using?
I'm not using any other norms.
Can you maybe scroll back to this definition then?
Which definition? You mean divergences?
Yeah.
What was the question?
I think for max relative entropy.
In the D infinity definition.
Yeah, D infinity definition, yeah. Yeah, it's here.
So what is that norm?
Sorry, yeah, you were right. This is the operator norm, just the largest eigenvalue. Okay? Yeah, thanks for the question. It's important. Yeah, but it's not going to appear again in the talk. Okay, so back to the properties. So you can verify these properties on these examples, and these properties are not independent of each other. For instance, if a divergence is monotone, then it implies stability, and it also implies an important property called isometric invariance, namely if you conjugate with an isometry in both states, then the value does not change. So this just means that if we embed both states in the same way into a larger Hilbert space, then the value of the divergence should not change. Okay, this is easy. And another property which is very closely related to monotonicity is so-called joint convexity, which is an absolutely central concept in studying these divergences, which means that if you take convex combinations in both arguments with the same weights, then we should have this convexity relation, which is a Jensen inequality, where this is just a probability distribution. Okay? And it turns out that joint convexity is more or less equivalent to monotonicity. Okay? And this is basically two classic results. The first part, I think, is due to Ullmann. And the statement is that if we have a divergence that is jointly convex and invariant under isometries, then it has to be monotone. And the proof fits into this slide, because we can write this channel in this time spring dilation form. So this is an isometry, this is just the partial trace. This isometric conjugation does not change the value of the divergence. And the trick is that we can write the partial trace as a convex combination of unitary conjugations. And these unitaries are the so-called discrete Weil operators, which are defined this way. And these X and Z are just higher dimensional generalizations of the Pauli X and Z operators. Okay. And I would like to comment briefly on this. So often if you see proofs using this idea, then the Haar measure is used, which is just as good to trace out things. But this is just much simpler because you don't have to know anything about Haar measures and the integration. It's just a finite convex combination. Okay? And in the opposite direction, we need to introduce some extra properties. So we say that a quantum divergence has the direct sum property if it can be expressed as a sum in the special situation when these rho i's and sigma i's are living on pairwise orthogonal subspaces, right? So this is the support projection of the span of the supports or the projection onto the span of the supports of rho I and sigma I. And if you take a different index, then it's going to be orthogonal to I. Okay? And in this case, we should have this sum property. And we say that it's homogeneous if multiplying by the same constant is just appears in the front. Okay? And the opposite direction of the previous statement is that if a divergence is monotone and homogeneous and it has the direct sum property, then it is also jointly convex. And this is an exercise for you to verify. You just have to apply monotonicity to these two classical quantum states, and that's it. Okay, so it's extremely simple. Right? So we have established that monotonicity and joint convexity are basically equivalent to each other. And with that, we have finished the first part of the talk. And in the next one, we will see how to, yeah.
Yes, so there was this property called log scaling where
Yes.
there are additional logs, but now we have the homogeneous.
Yeah, very good question. So if you take a homogeneous one and put a logarithm before, then you will get a log scaling thing. Basically, that's the idea. So we will have things which satisfy this homogeneity, and then we will put a logarithm before them, and then they will satisfy this logarithmic scaling.
Okay, so that's a different property.
It's a different property, but very closely related.
It doesn't have to be satisfied by the same.
Okay, thanks for this question. Okay, so now let's move on to define information measures from these divergences. The first one is entropy. So we will take a positive divergence, and we will assume this logarithmic scaling. You will see in a minute why. The notation is we will label Hilbert spaces with systems. They will correspond to Alice and Bob and whatever. And this absolute value A is just going to be the dimension of the Hilbert space, and this is going to be the maximally mixed state on this Hilbert space. Okay. And we define the entropy of a state on the system A by this formula. There are two conventions to write it. Either we use the notation H for entropy, we put the divergence here in the index, and either we put the state in the argument, or we put the system label in the argument and the state in the subscript. And there are two equivalent ways of defining it. It basically measures how far the state is from the maximally mixed state in this delta distance. Okay. And the reason why you can write them in these two forms is exactly because of this logarithmic scaling. Okay, so this is why it's useful and assumed here. And the interpretation of this quantity is the uncertainty about the system A in state rho. So if it is very close to the maximally mixed, then the uncertainty is very large. If it's very far away from it, then the uncertainty is small. So this is where this distance picture enters the interpretation. And one slight advantage of this first formula is that it also works in infinite dimension. Okay, so if you're in infinite dimension, then defining the maximally mixed state and putting this logarithm here might be a little bit complicated. And an easy exercise is that if you take the relative entropy, then you get exactly this well-known expression for the von Neumann entropy, which you have probably all seen before. And this is often denoted by S, but we will stick with this H notation. Okay, so this is the von Neumann entropy. Another exercise for these other quantities, you can also express explicitly the entropies, and they are called max entropy and min entropy, respectively. Okay. Right, and a few properties of these entropies. So if delta is positive, then it's obvious from this formula that the value of the entropy cannot be larger than the logarithm of the system, and equality is attained when the state is the maximally mixed state. And a very important property is this I cannot say it, of the entropy, which we call additivity because it's easier to pronounce, which just says that on a product state, we get the sum of the entropies. Okay. And if our divergence is monotone, then the entropy is going to be monotone, non-decreasing under unital CP-TP maps. So this is obvious from this formula. For instance, rank 1 projections are such examples. And I would like to elaborate a bit about this monotonicity property. Okay. So there is a very important concept called majorization that appears often in the context of entropies. And it's also very important in thermodynamics, this majorization and various generalizations of the concept of majorization. So we say that a state rho majorizes another state sigma, or that sigma is more mixed than rho, if the following relation holds, taking the decreasingly ordered eigenvalues of both operators, then summing up the m largest ones should be larger for rho than for sigma for every possible m. Okay. It's not completely clear why this is a good or interesting definition, but we will see it in a moment that it is. An exercise for you to check is that any pure state is majorized by any state, and any state is majorized by the maximally mixed state. So pure states are the least mixed states, and the maximally mixed state is the most mixed state according to this concept of mixedness. So this meets our intuition. And it turns out that if we have two states, then the following are equivalent, that rho majorizes sigma, and that we can map rho to sigma with a so-called random unitary channel, which again in turn is equivalent to being able to map rho to sigma with a unital CPTP map. Okay, so this is an exercise to verify. Most of it is very basic. For one direction, you should use the classical characterization of majorization, but that's also a very simple exercise. Okay. Sorry, once again?
In exercise 13, I think it's flipped.
It's flipped. Yeah, you're right, sorry. Yeah, you're absolutely right. So it should be the other way around, because now here I was thinking of mixedness, but indeed majorization goes in the opposite direction. Thank you very much for the comment. I will correct it on the slides. Indeed, very true. Okay. And more about this majorization property. So in general, we can try to characterize what kind of properties we are accepting from a function to call it an entropy. Okay. So we just have a function h on quantum states. And from the previous considerations, we see that it is monotone non-decreasing under unital CPTP maps, if and only if it is monotone non-increasing with respect to majorization. And this is called Schur concavity in matrix analysis. And in particular, such a function will take the smallest value on pure states and the largest value on the maximally mixed state. So this is something that we expect an entropy to do, okay, because it measures disorder. And another exercise for you is that any such function will take the same value on any pure state. Okay, so we don't have to specify that separately. And to call a function an entropy function, we would normally require that it is Schur concave and it satisfies the normalization that on pure states it is 0, and on the maximally mixed state it is the logarithm of the Hilbert space. And moreover, we want additivity also. Okay? And why is this Schur concavity called concavity? What does it have to do with concavity? It turns out that if a function is actually concave and unitarily invariant, then it is also Schur concave. But it's not true in the opposite direction. And if you start with a divergence that is unitarily invariant and convex in its first variable, then the corresponding entropy is going to satisfy this concavity property. Okay. So this was entropy. This was probably the easiest concept that we derived from a generalized divergence. And now let's move on to conditional entropy. So again, we start from a positive divergence that satisfies the logarithmic scaling. And we define the conditional delta entropy for a bipartite state with a very similar formula to the entropy, but now we will have an optimization for states on the second system. So up to here, it's the same definition as the entropy, but now we have a bipartite state, and here we can optimize in this state sigma. It will turn out later why this optimization is a good idea. And again, due to the logarithmic scaling, we can rewrite it in this formula, which is often useful. And similarly to the entropy, this measures how far the state is from a state where systems A and B are independent, and A is in the maximally mixed state. Okay, so that's the interpretation behind. Or is the uncertainty about system A given access to system B. And there is a variant of this notion where we don't take this optimization. Okay. It might look, I don't know which one looks more intuitive. We will occasionally use both of the definitions. Okay. So a few exercises related to conditional entropy. First of all, if the second system is trivial, then we get back the entropy. Okay. That's very simple. And also, if the joint state is a product state, which means that the systems are independent, then we again get back the entropy. Okay, so our uncertainty does not decrease if the two systems are independent. That's again very intuitive. A terminology for the conditional entropies derived from these divergences, they are called the conditional max entropy and conditional min entropy. And I put it into brackets because often this is omitted and they are just called max entropy and min entropy. And for these, there are no explicit formulas in general. The case of the relative entropy is different. If we start with the relative entropy, then we can actually find the unique optimizer here, which is just going to be the marginal. So these two variants are going to be the same. And this is just this expression that we have seen for the conditional Shannon entropy. So we take the entropy of the joint system and subtract the entropy of the second system. Okay. And it's part of the exercise to show that this can actually be negative on pure entangled states, which is kind of puzzling because we want this as a measure of uncertainty. So what does it mean that our uncertainty is negative? And one answer to this was given by Horodecki, Oppenheim, and Winter, who have found a so-called operational interpretation for this negativity of the conditional entropy as the entanglement cost in the state merging protocol. So I'm not going to describe the protocol here. You might have heard about it and then you know it already. If not, then maybe it doesn't make much sense to try to describe it now. But the important thing is that in this protocol, entanglement is consumed to achieve some task. And this entanglement cost is exactly this conditional entropy. And when it is negative, it means that we actually don't consume entanglement, but we gain entanglement from performing this task. Okay. Right? And the next important property is concavity. So if you start from a jointly convex divergence, then the corresponding conditional entropy is going to be concave in the state. It just means this relation here, which is a Jensen inequality. And one thing which is important about this is that if we have such a concave conditional entropy, and it is also additive and positive, then the conditional entropy is going to be non-negative on separable states. Okay, you can derive it from this concavity property. So indeed, this negative conditional entropy is really a quantum phenomenon. So this statement complements the previous one. Do both of the exercises. Okay. Right? Monotonicity of the entropy. If you start with a monotone divergence, then the corresponding conditional entropy is also going to be monotone in the following sense that, again, on the A system, we should act with a unital CPTP map, and on the B system, we can act with an arbitrary CPTP map. Okay, and if we consider the tensor product action of such a map, then we will see that the conditional entropy after the action is at least as large as the conditional entropy before. So this means that our uncertainty cannot decrease after the action of a noisy channel. And in particular, applying it to the partial trace shows that conditioning reduces uncertainty. So the conditional entropy cannot be larger than the entropy. And if we have more systems to condition on, then our uncertainty should decrease. Okay, so this is, again, very intuitive. Good. Right? And the next thing that we want from an information measure is that it should be additive. And if you start with an additive divergence, then we have seen that the entropy becomes additive, but this is not automatically true for the conditional entropy. What is true from the definition, what is obvious from the definition, is that it is super additive. So if we take two bipartite systems and couple them independently, then the corresponding conditional entropy is going to be at least as large as the sum of the individual conditional entropies. Okay, this is super additivity. And the question is, how do we prove additivity? And to prove it, we will prove additivity from a very interesting and very beautiful concept called duality of conditional entropy. Okay. So here's an exercise again for you. Consider the usual von Neumann conditional entropy and take a tripartite pure state, rho ABC. It is very easy to verify that the conditional entropy of A condition B is -1 the conditional entropy of A condition C. Okay. So this is again related to the possibility of negative conditional entropy. And motivated by this example, we introduce this definition of duality. So we say that if we have two functions that are defined on bipartite states, then they are dual to each other if this sum on different marginals of a pure state is always 0. Okay, so this is the same as what we have seen before. So the previous exercise shows you that the conditional von Neumann entropy is self-dual. Okay? And Another important example is that these conditional min and max entropies that we have considered before, they are dual to each other. Okay, so there is a very special relation between them. And this is, in fact, a special case of more general duality relations for conditional Rényi entropies, which I'm going to talk about in detail later. Okay. So why is it good if we have this duality? Again, this is for you to verify that if we have two such functions that are dual to each other and both of them are superadditive, then actually both of them are additive. Okay, so this is one way to derive additivity of conditional entropies. Right? And based on these previous considerations, we can now prove that the conditional min and max entropies are also additive. For the conditional von Neumann entropy, of course, we can get it from these considerations, but it also follows from the definition in a straightforward way. Okay? And one thing which is very nice about this duality concept is that most of the properties of these information quantities we can derive from this parent quantity, this divergence. But duality we cannot formulate on the level of divergences. So this is really something very specific to conditional entropies. Okay. Further exciting things about duality. One is that if two such functions are dual to each other and both of them are monotone, then we will get such bounds. Okay. So we have seen that conditioning reduces entropy. And if we apply this duality bond, then we will see that we also have a lower bound in terms of the entropy corresponding to this delta tilde. Okay? And this only depends on the first subsystem. And normally we start from positive divergences, and in this case, the entropies are smaller than the logarithm of the dimension. So we will get that the conditional entropy is upper bounded by the logarithm of the dimension of the first system and lower bounded by minus the logarithm. Okay? And what is nice about this is that apart from that it is independent of the state, it only depends on the first subsystem. Okay? And this is very important observation, for instance, to prove the Alitzky-Fanes continuity bound on conditional entropy, which in turn can be used to prove continuity of various channel capacities, which I'm not going to detail here, but this is an important application. Okay. And yet another beautiful thing about duality is that if we have two conditional entropy functions that are dual to each other and both of them are monotone under this special kind of maps, then obviously this sum is non-negative on arbitrary tripartite states, not only pure states. And the interpretation of this quantity is a certain monogamy of correlations. Okay. So if you consider the conditional von Neumann entropy, then we have seen that it is negative on entangled states, and it is actually the most negative on the maximally entangled state. So if this negative conditional entropy is large, that's going to mean that this other conditional entropy has to be very large. And if you think of the interpretation of this conditional entropy, then this means that the system A is close to decoupled from system C in such a state. So if there is strong correlations between parties A and B, there is very little correlation between parties A and C. So this is one interpretation of this duality relation. And the beautiful application of this is that it is possible to derive general tripartite uncertainty relations for dual conditional entropies defined from some divergences based only on certain assumptions of the properties of these things. So the first proof of the Massenhoofing uncertainty relation was quite involved mathematically, but this method developed in this paper is beautifully simple and only uses this duality relation, and we got such an uncertainty relation. The interpretation is that we make two measurements x and z on system A with output spaces x and z, and we look at the uncertainty about the outcome with quantum side information on system B or quantum side information on system C. And this cannot be arbitrarily low, these two conditional entropies, and it is lower bounded by a constant that only depends on the measurements. And this has very important applications in, for instance, cryptography, where you have to bound the the information that some eavesdropper has about a state, and you want it to be small. Okay, I think this much about conditional entropies and duality. And now let's move on to the mutual information. Is this pace that I'm going okay? Who thinks that this is too slow? Who thinks that this is too fast and already lost on the first 2 slides? Okay, who thinks this is a good pace? Okay, so the experts can follow the talk. Okay, so actually I can slow down. I'm going very well with the material. Do you have any questions at some point, at this point? Okay, so I can stop here, and everyone who feels lost can have a chance to catch up. So if you have some question, then yeah.
So I say the PTP map, so what's the PTP map?
Once again?
Well, what's the PTP map?
PTP is positive trace preserving.
I say so.
And CPTP is completely positive, and we also consider unital CPTP. Okay? Yes?
I don't even know what that formula is saying.
Once again?
I don't even know what that formula is saying. What does that symbol mean there?
Logarithmic scaling.
Yeah, that formula. Can you explain what it means?
This formula? Yeah, sure. I mean, this is what's coming now.
Okay.
I just stopped here to check if anyone is still following me. Yeah?
Please go back to the last slide.
This one?
Why the left one side is needed for unital?
Okay. That's a very good question. So well, maybe we should go back even to the definition of the entropy. That's the easiest to see. Oh, this is a bit slow. No, I don't go back to the entropy. Sorry, it's very far, the entropy. So why it's needed to be unital? Because you are acting on this state and also on this state. And we want to preserve this identity here. And for that, you need unitality. Okay, yeah?
I think for that exercise, I don't know if you need the monotonicity under unital on the A system to complete the exercise. Because I think you can just like purify and take a partial trace on the conditioning system.
Maybe.
Okay. But you know.
But in any case, all the quantities we will consider are either monotone and joint action or not. But maybe that's a good point. We should check that.
So I guess I have a question. So some of these infiniums that you have, you said that you don't actually know the state that satisfies them.
Yes.
So if you were to try and calculate it, how hard is this calculation?
Well, I mean, most of the time, these things are convex in their arguments. So this is some convex optimization. So it's, I don't know anything about numerics, but I was told that this is easy, or at least reasonably easy. But we will not try to compute these things. We are on a more abstract level. Sometimes you can compute, and sometimes you can say something about the optimal state, and that's going to be very important for things like additivity. We will see examples for that. Okay, yeah?
In the previous slide on equivalence between modularization and random unital channel, you also mentioned unital channel.
Yes.
But if I understand correctly, random unital channel and unital channels are different in general.
Yes. That's a very good point.
Clarify this point?
That's a very good point. Thank you for the question. So look at this statement. So, okay, so there's a classic result called Birkhoff-von Neumann theorem, which says that the extremal points of classical unital trace-preserving channels are exactly the permutations. So every unital channel can be decomposed as a convex combination of permutations. And this is not true in the quantum case. So it is not true that every unital completely positive trace-preserving map can be decomposed as a convex combination of unitary conjugations. So what's the caveat here? What am I claiming? Can someone resolve this apparent contradiction? So the statement is that it's not true that every unital CPTP map can be written in this form. Yet, here I'm stating that these two things are equivalent to each other. What's the problem? Or what's the resolution of this contradiction?
Well, maybe there will be different for different rows and sigmas.
Exactly. So these maps depend on the states. So I'm not claiming that if you find such a channel, then you can decompose it in this form. But for this particular pair of states, you can find such a channel and you can find such a channel as well. But for instance, it could happen that this channel is good for a certain set of pairs, but you need different random unitaries for different members of this set of, okay. Thanks for the solution and thanks for the question. It's very important. And yes?
Does every entropy have a divergence associated with it?
It depends how you define entropy. I mean, we did not define entropy. So you might say that we can try to come up with a list of criteria that we want them to satisfy. And then we want to see if we can derive them from some divergence. I haven't thought about this problem. It's a very interesting one, and I have no idea if anyone considered such a question. But it certainly makes sense that what kind of criteria should you impose on a function to call it entropy and to get it from a divergence? Okay. Any further questions? Who feels that he or she is a bit less lost now? Okay. Not too many people. Your question?
What is the property that distinguishes a unital CBT map from a general one?
It maps the identity to the identity. That's the very definition of unitarity. Okay? Yeah? Sorry? Yes. So why are they called max and min? That's the question, right? Okay, we will come to that. So they are actually special instances of a parametric family of entropies. And in this particular family, they are the largest and the smallest. That's where the name is coming from. Okay, any further questions? Okay, so I will try to go a little bit slower. And at any point, if you feel like you have a question, then please don't hesitate to interrupt. I mean, these questions were very good, and they connected to very interesting things. So I'm very happy to stop and discuss these things. Okay? Good. So let's continue our project of defining information measures from divergences. Where were we? We have defined entropy, conditional entropy. We discussed various properties of the conditional entropy. And now we are at mutual information, which is a very similar definition to conditional entropy. Again, we take a bipartite state, and we look at how far the state is from independent. Okay? And there are 4 different variants that might look a reasonable definition. So in the first one, there's the most accepted one, is we take this bipartite state, we keep its first marginal, and we see how far this state is from a product state where the first marginal is the same as for rho, and we optimize over the other state. Okay. There could be other definitions. We could optimize over the first marginal instead. Or, and I think this looks the most intuitively good one, that we could optimize over both of the marginals. So this would really measure how far the state is from the set of independent states, completely decoupled systems. Or alternatively, you can just keep the original marginals and do not optimize at all. Okay? And here's again an exercise for you, is that if you take this omega is relative entropy, then it doesn't matter which definition we take, they all coincide with each other, and you get this formula when you have the entropy of the first system, the entropy of the second system, minus the entropy of the joint system. Okay, this is probably very well known. But in general, if you take another divergence, they are going to be different. Okay. And it is not completely clear which one is the right definition. As I said, this is somehow the most used one. We will see some examples of it, but it's not completely decided which one is the right one. Okay. Yet another concept, if you have not had enough entropy quantities so far, I'm going to define a few more. So that is conditional von Neumann, conditional mutual information, von Neumann mutual information, which is, I mean, we start with indeed with the von Neumann entropy, and look at various modifications of the mutual information formula. So the mutual information formula was just the entropy of the sum of the entropies of the subsystems minus the entropy of the joint system. And here we just put a conditioning on a third system everywhere. Why not? An equivalent way of writing it is, again, we can express the mutual information as the difference of the entropy of A minus the entropy of A conditioned on B. And here we put an extra conditioning system C. And we have seen that if the divergence is monotone, which is true for the relative entropy, then this quantity is going to be non-negative. So this is the conditioning reduces uncertainty principle. And this actually is equivalent with the strong subadditivity of entropy. So if you write out this, then you will see that this is equivalent to this formula, this inequality here. And well, you have seen strong subadditivity in Patrick's tutorial, and many people agreed that this is probably the most important property of the von Neumann entropy. It has a long history, started with quantum statistical physics, and it has plenty of applications in quantum information theory. So if you got completely lost with all these different entropy quantities, then this is something to, well, to understand. Okay. And there are various important things related to this conditional mutual information. One thing is that equality in this inequality is satisfied if and only if the state is a so-called short quantum Markov chain. So this is some extension of the concept of Markovianity to the quantum domain. And recently, in the past few years, there has been a lot of activity in characterizing the situation when this inequality is satisfied not with equality, but almost with an equality, and this led to the concept of approximate quantum Markov chains and various generalizations of these concepts, but I'm not going to talk about that. And this quantity has an operational interpretation in the problem of quantum state redistribution, which I'm not going to explain now. Okay? So we can see that this is extremely important and very central in quantum information theory, but so far it is not really clear how to generalize it to other divergences. So there have been some proposals for conditional Rényi mutual informations by Mark and Kaushik Seshadris and Mario Berta, who have come up with a few proposals, but it's really not decided which is the right way to approach this problem. Okay. Good. So these have been a certain set of information measures that we have defined on this concept of distance, and they looked indeed very similar to each other. The entropy, the conditional entropy, the mutual information, and the conditional mutual information. Now I'm going to introduce yet another concept of information measure, which is based on this concept, but much more strongly on this interpretation of the divergence as a distance. And these are called the so-called divergence radii. So how do we define the divergence radius and center for a set of positive maps? So we take a set of positive semi-definite operators, and we define the delta radius in this way. Yeah, I don't know if I should attempt to write. Maybe you wouldn't see it anyway. So we just take the states from this set sigma, this capital sigma, and we take a state small sigma that we can vary. Okay. And we look at the worst case or the largest distance of each member of this set from this sigma, and we want to minimize this distance. Okay. And if sigma attains this infimum above, then we call it a delta center. Now, in general, we don't have an explicit formula for this. It is very easy to see that if the divergence is monotone, then we have this monotonicity property. If we want to consider it as a proper information measure, then this should be additive, but this is not at all clear again. And there is no general method to establish this. To make it a little bit less mysterious, if you consider a proper metric, so not these strange divergences, but a metric or a norm distance on this set, then this radius is indeed what you would call a radius. This is just the radius of the smallest circle that can be circumscribed around this sigma. And the center of this circle is going to be exactly this divergence center. Yeah? No, so this B of H plus is just all the positive semi-definite operators. That's all the states. Yeah. So we can take general positive semi-definite operators here, but we are optimizing over states only. Once again? Yeah, density operators, yeah. Yeah, sorry, yeah. So state and density operator is the same in my terminology. Yeah?
Are there any properties you want for the set sigma?
They are usually going to be the image of a channel.
Okay.
Any other question to this definition? Okay. Yeah?
Do we really need to use infimum instead of minimum?
That's a very good question. Normally, it's a minimum. So normally, this quantity will be, well, will be convex in this variable, and it's going to be lower semi-continuous. And this lower semi-continuity is what's important. So it's going to be a minimum. Okay. Any further questions? Yeah? Sorry, one second.
What do you mean by a circle?
Sorry, it should not be a circle, it should be a ball. So in a metric space, you can talk about balls, and you can look at the smallest ball that includes this set. So in a metric space, you can talk about a point and all the points which are less than a certain distance from this point. So then you have the concept of a ball, and you can ask how large is the smallest ball that includes this set. And this intuition is why we call this quantity a radius. Okay? Yeah, but this was my mistake. It should not be a circle. It should be a ball, indeed. Okay? Any other questions to it? This? Yeah?
So why do you use rho versus sigma versus the other way around?
Good question. Because this is what will become important later. So these are but this is a very good question. So in the end, we will be interested in the quantities that appear naturally in certain coding theorems. And with this convention, this will appear naturally and not with the other. Okay. Any other question? Okay. If not, then I will introduce the last information measure, which is going to be a modification of this divergence radius. Namely, we take a probability distribution, a finitely supported probability distribution on this set, and we define the p-weighted delta radius of this set, where instead of taking the maximum distance, we take the average distance from this center, and we want to minimize this average distance. Okay. And again, if sigma attains the infimum above, it's called a p-weighted delta center. again, it has monotonicity if delta is monotone. Normally, we don't have an explicit formula, and again, additivity is not obvious. And to make you a little bit more motivated in these quantities, if you take the usual relative entropy and you take a finite set, then the average state corresponding to this probability distribution is going to be the unique D1 center, and the corresponding radius is nothing else but the Hollywood quantity of this ensemble. Okay, so this is just another way to write the well-known Hollywood quantity of an ensemble of states. And moreover, this Hollywood quantity is nothing else but the conditional entropy in a classical quantum state. So if you have a set of states with certain probabilities, then you can construct this classical quantum state, look at the conditional entropy in it, and you will get exactly the Hollywood quantity. Shouldn't it be the mutual information?
Yeah.
Yeah, sorry, it's the mutual information. Yeah, I will correct this, sorry. But anyway, it is related to something that we have talked about before. So mutual information, this p-weighted relative entropy radius and the Hollywood quantity are the same. Okay, so various concepts that we have introduced turn out to be the same. Okay. And the last comment about these two different concepts of divergence ready, it is obvious from the definition that we have this relation for every possible p. And if our divergence is convex and lower semi-continuous in the second argument, then actually optimizing over this probability distribution will give us the non-weighted divergence radius. Okay. And the proof is very simple. So we have the definition of this delta radius here. It is clear that we can replace the supremum over all elements here to supremum over all finitely supported probability distributions. And then we can use something called the minimax theorem to actually interchange the infimum and the supremum. That's why it's called minimax theorem. And this is nothing else but the definition of the weighted radius. And this has found applications in establishing strong converse properties of various channel capacities. Okay, so this was the second part of the talk. And for the first half, I have a third part, which is going to be a little bit different, much more concrete, and you will see these quantities in action. Okay, but before moving on to that, now it's the time again to ask some questions, if you think something might help, yeah?
Can you go back to the definitions of the mutual?
Yes, sure. Sorry, it's the wrong direction. Yeah.
So with these four variants, what properties on the delta do we need to make them symmetric in A and B?
Oh. I guess in general they are not going to be symmetric. Well.
Because this double optimized version has a chance to be symmetric.
Well, okay. I mean, the flip operator is a unitary, right? It's a unitary conjugation. So if it's unitary invariant, then it's going to be symmetric. If you optimize over both of the marginals. If you are only optimizing over one of the marginals, then I guess it need not be. But still for the relative entropy, they are all the same, so it doesn't matter. But I think in general, if you use this definition or any of the two anti-symmetric definitions, then it's not going to be symmetric. If you use the two symmetric definitions, then it's going to be symmetric. Yeah. So. Any further questions? Yeah? Okay, yeah. This one? SH is inside BH plus, yeah. Yeah, I mean, so these are density operators, and they are all positive semi-definite by definition. No, it's just positive semi-definite, yeah. Okay.
Is there a simple example of a state that has high conditional mutual information?
High conditional mutual information. Well, of course, you can take the C system to be trivial and get a maximally entangled state that's going to have a high conditional mutual information because it's just the unconditional mutual information. Well, I guess, I mean, of course, if you go high with the dimension, then it's going to be, you can construct states with high conditional mutual information. But what would be a paradigmatic example as opposed to Markov states? Well, I would imagine something very highly entangled over all the parties. That would be my guess. Any other questions? Okay. If not, then relax a bit, clear your mind. Forget about all these frustrating abstract definitions. And we're going to move on to something more concrete and something probably much more familiar. Okay. And this is single-shot state discrimination and its relation to mean entropy. Okay. And I still have 20 minutes, so I'm going to go in a very relaxed pace. And at any point, if you have a question, then please feel free to interrupt. Okay. So we're starting something new. So wake up if you if you gave up already on divergences, and pay attention at least for the first slide. Okay. So the problem that we are considering is state discrimination, and more precisely, multiple single-shot and Bayesian state discrimination. I will explain what this means. And the problem is a very practical one. So there are two parties, Alice and Bob. They want to communicate classical information, and Alice wants to send Bob one of m possible messages using a quantum system. So what we can do, she can encode her message, any of these messages, into some state of the system. She can use a quantum channel to send it to Bob, and Bob receives the state or the system in a certain state. Here, already Alice is encoding, and the action of the channel is encoded in this row I. So this is what Bob receives at the end of the single-shot protocol. And in order to decide which message Alice has sent, he performs a POVM with the same set of outcomes as the labels of the messages. And if he gets outcome I, then he decides that Alice has sent message I. Okay, so this is a very simple and very relevant information theoretic problem. And if they moreover know that Alice sends the ith message with probability pi, then the quantity they want to optimize is the so-called optimal Bayesian success probability, or it's also called guessing probability, is that you look at the probability that Alice has sent the message I and Bob has received the outcome I. This is the probability of that. And you take this convex combination of these probabilities. So this is indeed a Bayesian probability. And you want to find the maximum of this. So this is the maximum probability of successful communication. Okay. This is called single-shot state discrimination. With single-shot because they don't repeat the procedure, multiple hypotheses because m can be an arbitrary finite number, and Bayesian error criterion because we are trying to optimize this. Okay. So this is the problem. Is it all clear what we are trying to establish? Okay, very good. So here's again the formula. This is the success probability or the guessing probability that they want to minimize. And here's an exercise for you. And I really recommend to do it. So assume that we are in the classical situation where all the row I commute. Alice and Bob can only use classical systems. So all the row i's can be diagonalized in the same basis. They are just functions on these labels of the basis. And then it turns out that, first of all, it is enough to consider measurement operators that are also diagonal in this basis. So the decoding procedure becomes classical also. And we say that the measurement is optimal if it's a so-called maximum likelihood measurement. Here's a formula for it. But basically it means that Bob looks at the side of the die that he has received, and his guess is for the message is the probability distribution that gives the largest probability for this outcome. So this is the usual maximum likelihood decision scheme. And it turns out that in this case, this optimal Bayesian error probability is nothing else but just the sum over x of this maximum function, where the maximum function is just the maximum of these weighted state values, weighted probability values. Okay. So this is all easy, simple computation with classical finite probability distributions. And this success probability, we can also write in this way. So if you're, again, reinterpreting functions as diagonal operators, then this is an operator which is diagonal in this given basis, and at each entry we have this maximum value. Okay. And if you take the trace of this diagonal operator, then you just get this sum. Okay? Okay, that's it. So in this case, we can define the maximum of many diagonal operators. And it has an importance in this state discrimination problem. Yeah?
So even if you are fixing the size of the message set and maximizing the probability of correctness, so you're not trying to find the rate at which you can communicate the
Sorry, so we're fixing the size of the message set, yes?
ordinality of M is fixed.
Yes, it's fixed.
Find the maximum probability.
The maximum is with respect to all possible measurements of Bob.
Yes, so you just want to find the maximum probability of the correct decision. That means it's not making it.
Sorry?
You want to find the maximum probability of the correct decision.
Yeah. The probability of the correct identification of the message. Yeah, the correct decision. Exactly.
So is the dual problem similar? Like if I say that it fixes the maximal probability of success to be something, let's say 196, and I want to find the maximum cardinality of message set.
Yes, sure. That would be the epsilon capacity of a noiseless channel. Yeah.
I think you have to minimize, or have to lower bounds, like the success probability has to be at least some amount, rather than upping
Yeah.
down.
Yeah. But that's what makes sense, yeah. Okay, any other questions? Okay, so this is the classical case. We can solve the classical case completely. You can solve the classical case completely. Okay. Now let's move over to the quantum case. So just a reminder that positive definiteness of an operator is defined by this formula. Well, I have already used the concept before, so maybe it's a bit too late to define it, but anyway. And the positive semi-definite order means that an operator is larger than another if the difference is a positive semi-definite operator. Okay, you are probably all very familiar with this. But here's a fun fact, which is usually not really emphasized, that if you take a finite set of self-adjoint operators, which are the equivalent of real-valued functions, then it usually does not have a maximal or a minimal element with respect to this positive semi-definite order. If you're a mathematician, then you can say this is not a lattice disorder. Okay. Whereas for functions, you can, of course, always define the maximum and the minimum, except for extremely special cases. And the even more surprising thing maybe is that even if you take all the operators to be diagonal in the same basis, there is still no minimum and maximum. Okay. Is there a contradiction? That before I said that for functions you always have a minimum and a maximum, and now I say that if you take diagonal operators, then you cannot find a minimum or a maximum. Well, it depends on how you define the set of upper bounds and lower bounds, right? So here's a very simple exercise again. Take two by two diagonal operators. You can even normalize them to be states, density operators. And then you can look at the lower bounds, the set of lower bounds to this operator, all the self-adjoint operators that are smaller than these two operators, or the set of upper bounds to these operators with respect to this positive semi-definite order. And you can easily verify that this set does not have a maximal element, so there is no minimum of the operators, and this set does not have a minimal element, so there is no maximum of these operators. Okay. And the resolution of this apparent contradiction before is that you define the set of lower bounds for all possible self-adjoint operators, and not only for operators which are diagonal in the same basis. And likewise for the set of upper bounds. Okay. So this order is indeed very different from the usual order of numbers and functions. But here's a theorem, is that if you take again a finite set of self-adjoint operators, we have seen that there is no maximum of them with respect to positive semi-definite order. But if you change the order, the definition of the order, then there is a unique maximal element. Namely, you can look at all the upper bounds with respect to the positive semi-definite order. So you keep the order here. And then there is a unique element with minimal trace. So it's not minimal in the sense of positive semi-definite order, but it's minimal in the sense of taking the trace. Okay. And this element we will denote as the trace maximum of these operators. Okay. And similarly, you can define the trace minimum of the operators. Okay. And an exercise is that if all these operators commute, then this trace maximum is actually going to be the usual entry-wise maximum. So they all commute, so they are all diagonal in the same basis. And the element with the smallest trace in the set of upper bounds is actually going to be the entry-wise maximum. Okay. So this concept really generalizes the usual maximum. And another exercise connecting it back to the information measures is that if you normalize this maximal element, you divide it by the trace, then you will actually get this unique d-infinity star center. Okay, so this is this divergence center of this set of operators if they are all positive semi-definite. And the logarithm of the trace of this maximal element will be the divergence radius. Okay. So here we connect back to this abstract concept that we have introduced before. And why it is important for our problem is due to a classic result by Yuan, Kennedy, and Lux from 1975, who has shown that if you look at this optimal guessing probability, this optimal success probability of Bob identifying Alice's messages, then this is nothing else but the trace of this trace maximum of these operators, of the weighted density operators. Now you can write this in a different way. I mean, this is just the definition of this trace maximum. And here you have positive semi-definite operators. You can normalize them to be states and take their trace separately. And then you get a double optimization over states and positive numbers. And this condition becomes of this form, which is nothing else but the exponent of the minimum over all states, the supremum over I, this expression, which, as you can recognize immediately, is this d-infinity star radius of this set of operators. So again, we have this very practical problem of communication, single-shot communication. We want to optimize the success probability. And it turns out that this can be expressed explicitly as the infinity star radius of this set of weighted density operators. Yes?
I learned from Mulevo that this maximum is not increasing, right?
It should be.
It's not increasing.
It's not, okay. That would be extremely surprising because, well, if you increase an operator, then the set of upper bounds should decrease, no?
Yes, but there is a problem.
There is a problem.
That's what Mulevo told me. He knows that since 74.
Okay. Okay, well, thanks a lot for this comment.
That's the difference, right? The maximum function jumps.
Okay. That's very interesting. Thanks. You have a concrete example, maybe?
So, yeah.
Okay. Okay, well, maybe you can write it on the board in the break and we can all learn it. Okay, thanks for the comment. So what we see here is, especially if you take all the probabilities to be equal, then the optimal success probability is nothing else than 1 over the number of messages times exponent of the infinity star radius of this set of states that Alice is using for her encoding, or what Bob is receiving. So if you thought that these concepts are something extremely abstract and who knows whether they have anything to do with anything real, then this is an example that they are actually very closely connected to a very important and basic problem. Okay? And yet another way to write this expression here is to write it as the exponent of minus the conditional infinity entropy of A condition B in a classical quantum state where you take the code states and you create this classical quantum state here. So this, in turn, is an operational interpretation of the conditional min entropy, which is due to Koenig, Renner, and Schaffner. And if you want to understand it in even more detail, then you can think of it as having this composite system, this classical quantum state, and one player, Bob, has to find out the classical label. And he knows that the state is this, but he only has access to this system, and he can make measurements on this system. And so his guessing probability of the identity of I is the conditional entropy, conditional infinity entropy, or expressed in terms of that, when he has access to this extra system. So is the optimal probability of correctly guessing the classical value, the label I, based on the quantum side information in system B. And if you don't have side information, if you only have this classical state, then what you get from this, we have discussed that the conditional entropy just becomes the entropy. So you get this formula. And in this case, this is nothing else than the largest probability in this probability distribution. So this would be your guess if you don't have any other information. You have to guess which outcome of a random experiment happened, and your guess would be the one with the largest probability. Okay. So here again we see entropies in action, or some kind of very, very explicit operational interpretation of these entropies. Bless you. Okay, and in this paper they also gave operational interpretation for the conditional infinity entropy, not only for classical quantum state, but general bipartite quantum states, but that I'm not going to discuss. And let's see how much time I have. Okay. So I think I'm going to skip this geometric problem, even though it is very nice. And in the last 4 minutes, I'm going to consider the special case of binary state discrimination. So before we had m different messages. It was a multi-hypothesis testing problem. Here we only have 2 messages. And the problem in this case is that we have 2 positive semi-definite operators. These are the states multiplied by the probabilities. And this is the guessing probability if t and 1 minus t is a POVM measurement. This is what we want to maximize. And without using the UN-Kennedy-Lux result, you can establish that this optimal probability is indeed the trace of the trace maximum of these 2 operators. And this case is special because you can actually give a formula for this trace maximum of these 2 operators. You can choose either of these 3 equivalent formulas. So we can write up explicitly the trace maximum in this case. And from this, you get that the optimal guessing probability for rho 1 against rho 2, when the priors are equal, 1/2, can be expressed by this formula, which is nothing else but this formula translated to our case. Okay. And this gives an operational interpretation of the trace norm. So this is why the trace norm is distinguished among other norms, and we measure the distance of states. And as a corollary, in this case, you can explicitly write up this d infinity star center. It's going to look like this. And you can explicitly write up this d infinity star radius, and it's going to be a logarithm of this guessing probability. So you can write up these abstract quantities very explicitly. And these have very important applications. You can derive improved Orlitzky-Furness inequalities for the continuity of the conditional von Neumann entropy. Recently, Andreas Winter had a very nice paper about this. Okay. And from this, you can immediately derive the optimal error probability, which is just 1 minus the optimal success probability. So you can, again, express it in terms of the trace norm distance. And what we are going to be concerned with in the second half is what is the asymptotics of this quantity if you are taking many copies. So basically, Alice and Bob has the same communication problem, but now Alice can send the same message several times, and we want to know how quickly the error probability is decreasing with the number of repetitions. Okay, so this was the plan for the first half. We are exactly on time. I'm sorry if it was too fast or too abstract in the first half. If you have any questions now or later in the second half, don't hesitate to ask. Yes, Mark has one.
Can you go back to the previous slide?
Sure.
Yeah, the bottom part.
Yeah.
I was wondering if you could say more about this. So you're saying the delta infinity center is connected to continuity. Is that what you're saying?
It's connected to what?
What part of this is connected to the continuity results in your paper and
Okay, that's a very technical thing. I was planning to include it, but there's too much material already, so I can explain that. Yeah, I can. I'm not sure it makes sense to explain it publicly. It's a very technical thing, but very important. It's crucial for the proof. So basically, the origin.
In these proofs, they find a state that's somehow a convex combination of the states of interest.
So now that you insist, it gives me an excuse to go back to this problem that I skipped.
This is it, right?
So this is it indeed. So all these infinity divergence, radii, and center are connected to the following geometric problem. And no, you cannot escape. I will explain it. So we have a set of states. And what we want to find is another set of states such that every state has a pair, a rho I prime, with the property that taking convex combinations of the original state and the pair with a certain weight q gives the same state in between, independent of the index I. Okay. And what you want is to find this largest q, this largest convex weight. And it turns out that minus logarithm of this largest weight is again nothing else but the infinity radius of this set of states. And this average state, which is the same for every index, is nothing else but the d infinity radius, or divergence center, sorry. And why it's important is that this kind of construction is very important, was very important in the original proof of the Orlitzky-Furness inequality, but they used a suboptimal state. They didn't use this infinity center, they used some other random ad hoc choice. And what we realized in this paper is that you should actually choose this, and then you get improved constants. And then Andreas improved it even further by some extra coupling techniques. Does it answer your question? Okay. Any other questions from non-experts? Well, if not, then this was the first half. Thanks a lot for your attention, and hope you can recover in the break.